Let us switch over to the next number, that is problem number 17. A wire of length 1 meter fixed at one end has a sphere attached to it at the other end. The sphere is projected horizontally with a velocity root of 9g. When it describes a vertical circle, the ratio of elongations of the wire when the sphere is at the top and at the bottom of the circle is. The options are given 2:5, first option. Second option is 5:2. Third option is given 3:5 and fourth option is given 5:3. A wonderful concept which of course is based on the motion of a body along a vertical circle. We know pretty well whenever a body is just moving along a vertical circle, the tension in the string when the body is at the highest point on the vertical circle, that is going to be minimum. And the same tension in the string is maximum when the body is right at the bottom of the vertical circle. So based on these two values, the minimum and maximum values of tensions, he is asking you the ratio of elongations produced in the string as such. So if you just look at this question number 17, what we are talking about, if I consider this is the vertical circle and this is the sphere what he is talking about, and you can definitely understand this is the highest point and this one is the lowest point on the vertical circle over here. One thing you can definitely understand when this is the case, it is given a horizontal velocity of root of 9g. So you can definitely understand this is the velocity at the bottom. What would be the velocity of this particular body when it is at the top? I just want to first of all, because we know very well the tension at the highest point, if I consider at the topmost point, like this is mv square by r minus mg, that is the formula. What is this v now? V at the topmost point on the vertical circle. Likewise, when I just want tension when it is at the bottommost point, that I can write it this way, mvb square by r plus mg. That is mv square by r plus mg, the tension is going to be maximum when it is at the bottom. If I calculate these two values, elongation is directly proportional to tension. So according to that concept, we directly can take the ratio of elongations in the string. So that's what actually we people have to do. When you are giving some horizontal velocity as Vb to that body, when it is completing a vertical circle like this, you can certainly understand, according to law of conservation of energy, the kinetic energy of this body is going to be lost when it is going up, whereas it gains potential energy. If I take the radius of this circle as r, what is the total height raised by the body? That is going to be equal to the diameter, which is 2r. So we can directly understand this r value is given as 1 meter here in the problem. That is true. Afterwards we can calculate, there is nothing in that. So let us first of all apply law of conservation of energy. So what we can understand now in this case is, according to the law of conservation of energy, according to law of conservation of energy, energy at this point is equal to the kinetic energy plus potential energy at this particular point. So what is this kinetic energy over here? Half m into v square, that is now 9g, is equal to mg h, that is 2r, plus half m velocity at the topmost point square. You can cut this m throughout, first concept. Then what can you understand here? You see, this r being 1, this now becomes 2g. This is Vt square by 2 and this one is 9g by 2. So you can directly write Vt square, V at the topmost point square, that's what I am talking about. That is equal to this 9g minus 4g. It now becomes 5g. Then what is the velocity at the topmost point now? Root 5g. That is the value first you have to adopt. Then what we can understand here, look at the next case. Tension at the top, that is nothing other than m v at the top square by r minus mg. What is the velocity at the highest point? We people have got it, root 5g you have got. Now you can write this one 5g, 5mg minus mg, because r is 1. That now becomes 4mg. Exactly in the same manner, tension at the bottom, let us calculate. That is m into v at the bottom square by r plus mg. You can certainly understand v at the bottom already has been given as root 9g. Square it up. 9mg plus mg, because r is 1. We can understand. So this now becomes 10 mg as such. And what is the ratio he is asking? He is asking us to calculate the ratio of elongations produced. That too, what is the order? At the top and at the bottommost points. So we can write elongation when the bob is at the top is to elongation when the bob is at the bottom. That now is going to be the tension when the bob is at the top is to the tension when the bob is at the bottom. So this is 4:10, which now can be written 2:5. That is going to be the correct option for us. 2:5, if you look at this particular ratio, is tallying with the very first option which has been provided to us. Therefore, the answer for this particular problem is A, according to the given 4 options for us. So it's a wonderful model question here. Elasticity, actually we people are dealing with the elongation related to the tension in the string when the body is moving along the vertical circle. That's what actually is the question. So if you can identify this model, right, and if you remember this is one of the best models what we have, which is relating this elasticity concept with the vertical circular motion of a body. That is problem number 17 for us. Look at the next number then, that is problem 18. Uniform pressure P is exerted on all sides of a solid cube at a temperature 0 degrees centigrade. In order to bring the volume of the cube to the original volume, the temperature of the cube must be increased by T degrees centigrade. It's a very clear-cut concept here. When you are applying pressure on all the sides, then naturally volume is going to be reduced. In order to bring back this volume to its normal value or initial value, we just have to heat it up uniformly to a temperature T degrees centigrade. That's what has been mentioned in the problem. If alpha is coefficient of linear expansion and K the bulk modulus of the material of the cube, then T is equal to how much? That means to what temperature you are supposed to increase that particular sphere, that cube, what he is talking about. So that value we just want. To what temperature the cube is now being raised to bring back its original volume. That's the point. So options are given this way. The very first option is given as 3p by k alpha. Second option is given as p by 2 alpha into K. Third option is given P by 3 alpha into K. And fourth option is simply P by alpha times K. So what is the correct option out of it? First and foremost, we have to think of what is the formula for bulk modulus, because he is applying pressure on the body. So we can say bulk modulus K is equal to pressure over change in volume by original volume. That is what actually is the formula, what we all know that. But now the question here you have to understand is, we know this pressure as it is, you write it. Delta V by V, that is fractional change in volume of the cube. We have a formula, delta V by V is equal to gamma times delta T, where gamma is coefficient of cubical expansion of the material of the cube. That is volume expansion also we can call it. So if you take this, you can repeat the same formula this way, rewrite in a different manner. Gamma can be written as 3 alpha into what is delta T now here? T minus 0. Why? Because you can understand the final temperature is T degrees and initial temperature is 0 degrees. That is what has been given there. So in fact T minus 0, you need not write it, you can directly write it as T itself. What is the value of T? That is the question asked. So you can write that one P by 3 alpha into K. Whatever the value you get in degrees, you can get that answer. So P by 3 alpha into K. That is actually the calculated value for T what he is talking about in the problem. If you look at the options there, the same option is tallied with the third option given there. It's P by 3 alpha into K. That is what actually has been given there. Therefore, the correct answer for this one is going to be the third option, which is C, according to this problem. Only point we need to understand is this delta V by V, that is to be called coefficient of cubical expansion of that solid, which can be written as gamma into delta T. That is change in volume by original volume. That of course is called fractional change in volume, which can be written as coefficient of cubical expansion into delta T. That is the variation in temperature over there. So this is actually the model which of course we have taken up in problem number 18, which is also one of the good models what we have of this topic. Look to the next number, problem 19. A solid sphere of radius r made of material of bulk modulus K is surrounded by a liquid in a cylindrical container. A massless piston of area capital A floats on the surface of the liquid. When a mass small m is placed on the piston to compress the liquid, the fractional change in the radius of the sphere, that is what is given as delta R by R, is how much? Now here the options are given this way. First option is mg by A into K. And second option is mg divided by 3ak, and third option is mg by A, and fourth option is 3mg by A into K. So once again what he is talking about, you look at again based on bulk modulus, again based on the variation in volume of that particular body. In this case the body is a spherical body. So what we can understand here again, K is equal to P by delta V by capital V. Now what is his question, you see? His question is what is delta R by R? That is the concept. Now you can write this pressure as force per unit area by dV by V. or delta V by V, whatever you write, delta V by V, that is nothing other than fractional change in volume of that spherical body what he is talking about. Now we can rewrite the same this way. Delta V by V is now going to be F by A into K. Till that extent fine. But we just want the value of delta R by R. We can all understand well, for a sphere, volume is going to be 4 by 3 pi r cube. If I take r as the radius of the spherical body, volume is 4 by 3 pi r cube, we all know that point well. Wherefrom I can now write delta V by V will now be 3 times delta R by R. That only he is asking you to write like this, delta R by R like this. Then what can we understand in this case? Delta R by R, is it not 1/3 of delta V by V now? Is it not delta V by V this much? F can be written as mg by A into K. Now substitute the values over here. So you be getting mg by 3AK in the denominator. This is the final result what we can obtain from this calculation. So you people are getting mg by 3 times A into K, A being area of cross section of the piston what he is talking about, and K being bulk modulus of the material of the sphere he is talking about. So if you look at this one, same option, same value has been given in the second option for you. Look at mg by 3AK. So correct answer for this one is now going to be B as such. That is the point we have to remember. So once again, this model is slightly different from the previous one what we have discussed. So look at both the models thoroughly, and both are equally good models for us. So remember them till the examination, that's the point. So this is problem number 19, of which the correct option is B for us. Look at the next number, which also has been one of the very commonly asked models. Let me read it out. 8 meter long rubber string having density 1.5 into 10 cube kg per meter cube and Young's modulus 5 into 10 power 6 Newton per meter square is suspended from the ceiling of a room. This is a rubber string is suspended. The increase in its length due to its own weight is how much? That means no weight has been attached at the other end of the string. Mind this point. The weight of the string itself is elongating the string after some time. What is going to be the elongation produced in the string due to its own weight? That is what is the question asked. And of course he has given us in brackets, take the value of G as 10 meter per second square. That's for the calculation to be easier, nothing more. And first option is given as 9.6 into 10 power minus 2 meter. Second option is 19.2 into 10 power minus 5 meter. Third option is 9.6 into 10 power minus 3 meter. And fourth option is 9.6 meter. These are the 4 options provided to us. Now we have to decide which is the correct option out of the 4. A string, of course, we people are taking up here. This is a string made up of rubber. Its length, of course, is given 8 meter. That's what is given in the problem. This as capital L I can take. And of course, he has given its density. He has given even Young's modulus of that. Due to its own weight, what is the elongation produced in the string? That is the question. So let us write first of all the general equation for elongation. It is FL by AY. No doubt you can all understand F now becomes mg into L by A being pi r square into y. That is actually the case. But all of you can understand in this case, when I write this mass in terms of volume and density, mass can be written as the product of volume and density, we know that. Therefore, we can write this volume as pi r square L into density, that is rho, into G into L by pi r square into y. This is the general equation. But remember one point very thoroughly here. When you are attaching a body here with respect to the center of mass of that weight, we people used to measure the effective length of the string. All of you can understand this point. I repeat once again. When we are attaching a weight at the end with respect to the center of mass of that weight, we people used to estimate what is the effective length of the string. But here no weight is attached. Due to its own weight, we people just have to consider the effective length now. All of us, we know very well, any body if you consider, its weight is going to act at center of gravity. Its effective mass is going to act at center of mass. With respect to this particular point, we people have to take the effective length now. So what is effective length in this particular case? From the point of suspension to the center of mass of the same string, whatever the length we are finding, that length is to be considered as the effective length of the string now. So what should we write in place of L now? It should be written as L by 2. This is the important most feature of this problem. Otherwise, problem has nothing special. So if you look at once again, this L should now be written as L by 2. But be a little careful with this volume part. While calculating volume, you are not supposed to take L by 2. If you take L by 2, you are measuring only half of the volume of the entire body. That's not correct. When we want its mass totally, total volume into density, we have to write not half of the value. Therefore, here it should not be written L by 2, but here the effective length should be taken with reference to the center of mass of the particular body which is suspended there. So you can write this is L by 2 and pi r square getting cancelled over here. What is now left over? Just look at rho L square G by 2y. That is the formula ultimately. Rho the density, L the length, G acceleration due to gravity, and y is Young's modulus, what has been provided to us as 5 into 10 power 6 here. Let us write the equation, the values in this equation please. E, the elongation is now going to be, what is the density as given? 1.5 into 10 cube into L square being 8 square, which is 64. G is already given as 10 in the problem, we know that. Divided by twice, what is Young's modulus of the material of that string he has given? 5 into 10 power 6 Newton per meter square given. So write 5 into 10 power 6 Newton per meter square. Now first you can cut this 0 with this point, and 5 goes here 3 times. 2 cancels here 32 times. 3 times 32 now becomes 96. That's okay. This 10 power 3 cancels here 10 cube times. If it comes up into 10 power minus 3, you are left with that. That of course you can rewrite it like this also, 9.6 into 10 power minus 2 meter. This is the very first option which has been given to us in the problem. So the correct answer for this one is now going to be A. This is the case for this. So in case if they ask any application like this, due to its own weight, what is the elongation produced in a string of length L? then directly you can remember this formula hereafter, rho L square G by twice Y. Rho being the density of its material, L its length, G acceleration due to gravity, and Y is Young's modulus of the material of that string, what has been described there in the problem. So if you remember this formula directly, you can work it out without much of a delay of time. So that is the concept. This is problem number 20, for which the correct answer tallies with first option, 9.6 into 10 power minus 2 meter as such.